I will go to introduce Timo Prusti. So Timo Prusti has joined ESA in 1993 and has worked on had work on ISO and Herschel, and he's involved in Gaia since 2007, and he's the project scientist, so that's one of the most important persons in the Gaia mission. His scientific interests is directly connected to this set of lectures. He has been interested in the initial mass function and also in disks, structure of disk and evolution of around young stars. So I let you now the stage, and I'm pleased to hear you as well.
Thank you, Laurent. So it's a pleasure to be here. Thank you very much for the organizers for the invitation. As Laurent said, it's very much a topic which I personally like myself as well. So I'm happy to give the lecture, and I'm maybe even more happy then to take a seat at the other side and listen to other topics of this school to learn something what is happening in the field. I was looking at the participant list of this meeting, and I saw there were some familiar names who know a lot about Gaia, but most of the names I didn't recognize myself, so I think that maybe I have to do a mixture of, I'm going to introduce you mostly generic things of Gaia, and then I have a couple of things which are really related to star clusters and trying to feed into this specific topic of this meeting. So let me just start with the summary. So Gaia is there not alone. I mean, it's really building on the Hipparcos heritage and continuing of astrometry where Hipparcos left it. It's not only astrometry, it's also photometry and spectroscopy. So it's a complete package what we are going to get from Gaia. Current schedule for launch 2013. And it's a peculiar mission in the sense that unlike in many satellites, we have instruments which are built by scientists in scientific institutes. In Gaia, everything, satellite, including payload, everything is built by industry, while the data processing is done by scientific community, the Data Processing Analysis Consortium of Gaia. So obviously there is a sort of worry to do. How does all the knowledge what industry has now, because they are building it, move into the people who are doing the data processing? All the things which are not documented, how do you get that one carried over? Data releases, we try to get the science alerts out as early as possible. Clearly there will be a beginning period, a few months, that you have to verify first that you are not going to overwhelm. I mean, I will come later to the numbers, but just a typical number which I read somewhere, I haven't really checked it. 8 supernova every day. That's what Gaia will see. And then you can imagine all kind of other numbers which are coming. So very quickly you come with 1 million alerts per day. So you have to think a little bit what you are going to alert and what you are not going to alert. But I think in the end everyone is looking forward for the intermediate releases. There is an intrinsic problem with astrometry, parallax, based on the yearly movement. So you have, in any case, you have 1 year time to get the parallax sorted out. And you actually need a little bit more time because you want to disentangle proper motion and parallax. So you need the time to do it, to get the observations. So the first data release in a scenario we have now, so 22 months after the launch, and 28 we try to get really, start to get parallaxes, 28 months after the launch, parallaxes out. I see people are writing notes. Web pages, everything, all the numbers I'm going to give are going to be on these web pages. So if you can also search Gaia ESA and you will find the web page. So, and much more. So don't spend too much time in scribbling down what is being presented. All the plots are also available. Science topics. It's not only a very limited area which Gaia is going to address. Really the main thing is the structure and dynamics of our Milky Way galaxy. Obviously, if you know where the stars are, and if you know where they are going to, you get the structure, you get the dynamics. if you combine that with photometric and spectroscopy information, you can start to look at the stellar properties. You can start to talk about star formation in global scale in our Milky Way galaxy. And obviously, if you do get the distances, I mean, most of the time, if you do any kind of work and trying to figure out what the stellar parameters are, you are stuck with the distance and the error in the distance. So if you get the distances pinned down, obviously, you are going to make a major step progress in stellar astrophysics. Binaries, again, a complete census, simply because the spatial resolution is unique for the whole sky. I mean, you can do Gaia resolution with the Hubble Space Telescope, but here you get the full sky coverage. So it's a census of everything. In the solar neighborhood, it will be a very accurate census of something like brown dwarfs, and a little bit larger scale, all the exoplanetary systems. The expectation is some 5,000 exoplanetary systems with astrometric methods. These are going to be not really the hot topic of Earth-like planets. It's going to be sort of Jupiter-like planets, but in longer orbits. That's where Gaia is going to be very strong, sort of 1 year, 2 year orbit, which is a parameter space which is not so well known. Our solar system, we will get the asteroid ephemerides to accuracies which cannot be done from the ground, and also Gaia can look to an angle, so looking like inner Earth asteroids, which are very poorly known population. And moving out, I mean, Gaia is going to observe point sources. Well, galaxies are sometimes point sources, sometimes a little bit extended. If they are point-like enough, they will be detected, and we get the data. We expect few million galaxies will be picked up by Gaia. So it's of course not the main thing, but if you have a sample of homogeneous photometry for a few million galaxies, I'm sure it's a valuable sample to do studies. 500,000 quasars, so you don't do the quasar science with the sample again, but the key thing is that the reference system, reference frame or coordinate system is based on quasars in radio wavelengths, and now Gaia is going to observe a number of these ones in optical wavelengths. So Gaia is going to be able to make its own reference system based on optical data, which is as accurate as the radio data, but much denser. So you have Gaia stars everywhere. So we have a reference frame which is really rock solid for future astronomy. And you can tie them together because Gaia will see the quasars. So you can put these two systems in one frame. And finally, fundamental physics, general relativity. And when you go to micro-arcsecond accuracies, there is no photon coming to Gaia straight. They are all curling and curving around before they hit it. So in order to calculate where did you get the photon, everything has to be corrected in a relativistic sense. First you have to do a relativistic correction. Where did the photon come from? Only then you can say where the star is. But then when you have sorted this one out, then you start to okay, I have quite some redundancy. Let's see how close I can pin down some general relativistic parameters. So there are experiments planned to be done with the global Gaia dataset. Okay, a few words of Hipparcos magnitude limits. Hipparcos was up to 12th magnitude, completeness a little bit at the brighter end. Gaia is going to be from 6 to 20 magnitudes. So if you ever tell any amateur astronomer of Gaia or amateur or general public, it's a bit sad. So the night sky, all the stars what you see, none of them can be measured by Gaia. So those stars will be in the future the stars from which we know the least because they were too bright. The increase in numbers is from Hipparcos 120,000, one goes to 1 billion. We go from milliarcsecond domain to microarcsecond domain. And I think it's one of the big lessons learned from Hipparcos. When people started to analyze the Hipparcos data, we didn't have radial velocities. So ever since, there has been programs measuring radial velocities for Hipparcos stars. I mean, that's only 120,000 stars. So very quickly you realize that if you want to do something similar to Gaia, of course you can do it from the ground, but it will never get done. So the only way to do it is to do it directly at the same time. And of course, you run out of photons, so you cannot do it for billion stars, but you're going to do it for 150 million objects. And another thing is that Gaia will detect its sky. It has no knowledge where the stars are. It will just detect and observe. Everything to 20th magnitude is going to be passed by. So a little bit of how it works. 2 telescopes, 1 focal plane, where the 2 telescope field of view are combined. And the idea being that these 2 telescopes, the angle between them is very well fixed. So you're looking to 2 different directions, and this way you connect the full sky. So you're going to get the full sky accuracy because you do all the combinations of pairs of stars over the whole sky. So you are not trying to do astrometry in a local field and then sort of carry it over the whole sky. You tie it with a large angle, which gives you stability. Actually, that's the only way to do absolute astrometry. And what does it look like? It's a real thing. It's a silicon carbide optical torus where the mirrors, all the instruments and the focal plane are attached. And just to show that it's ready, all mirrors are mounted, aligned, and this is a little bit busy picture with a lot of ground equipment as well, but it exists. Focal plane, CCDs, 106 CCDs. What is the basic idea? First we have SkyMapper CCDs, and these are really actually the only CCDs which are fully red, and that's for the detection. So you want to detect the whole sky. There's 1 row for telescope 1, 1 row for telescope 2, and the idea is that after this one, everything is combined in the rest of the focal plane. So this is the moment when you do the bookkeeping. Which star, not only which star did I see and detect, I want to observe with the rest of the field, but also from which telescope it came. That's happening at the SkyMapper stage. After the SkyMapper detection, it makes a decision which stars are going to be observed. So the rest of the field, the computer on board is keeping track. Where are those stars on the CCDs which I want to actually measure? And most of the CCDs are flushed. Actually, so you do observe, you have a full sky, but it's flushed. And only those ones which you decided at the very early stage that I'm going to do, you are going to downlink. And the method how observing is done, because Gaia is a scanning satellite, the stars are sort of moving on the focal plane. What you're doing, you're reading the CCDs at the same speed as the spacecraft is moving. So you keep the point spread function at the optimum size all the time. So it's the Sloan survey idea of mapping. Pixel size, we don't have square pixels, 60 milliarc second by about 180 milliarc seconds. Most of the field is for astrometry, and then you have for the photometry, you have a row of blue photometer CCDs, red photometer CCDs, and the last part are the radial velocity spectrometer CCDs. I think I said everything here I wanted. Just to show again, we have a focal plane, all the CCDs are ready. This is actually quite an old picture, but at a certain point when the spacecraft starts to be assembled together, everything starts to get behind something. So the nicest pictures of Gaia, they are now taken already. I can show them. After now, it's from photographic point of view, it's only downhill because everything goes behind baffles and all other things. Photometer, actually very simple, prisms. In 2 prisms, so blue and red photometer covering combined from 330 to 1000 nanometers. And actually, so the photometric instrument is very simple. That's it. It's a prism. And so this one is the red prism, because it's reflecting the blue light. And that's the blue prism reflecting the red light. So they exist. And this is a little bit of hint when you start to put things together, so that you see the CCDs and you see also the prisms here in the box. So they are all getting in their places and aligned. Spectrometer, resolution of 11,500 in the red area, 847, 4 nanometers. So here you of course always you do a compromise which wavelength you choose. So this is clearly good for cool stars, a little bit less good for hot stars. That's a little bit more complicated instrument. So it's a sort of box which you can just have in your hands, 27 kilos. It has swung grating, filter, 2 prisms, 2 wedge lenses, optically a very compact instrument. Also spreading the light, which is then observed with the CCDs. It's already a big instrument, so that's there you see the link why in the CCD field you had for astrometry and photometry you had the full length, and for spectroscopy only a narrow one. It's compatible with the instrument size. When you start to make big glass pieces, it starts to be more and more difficult if you try to make really huge spectrometer. It doesn't quite work out.
How big is that?
This one. 30 kilos. Yeah, it's very compact, so the lenses are really extremely close by to each other. And it's also because it's at the edge of the field, so it's doing some correction to the telescope. So it fits only to Gaia. The scanning law. So there is one thing what you want to in an astrometry mission, you want a stable satellite. So how do you do stable? You have to worry about the thermal conductivity and all this. You have to limit the input always to constant. So how to do it? You put Gaia to 45 degrees to the sun. So it's always at 45-degree angle with respect to the sun. It's not for the scanning optimum. You would like to have a different angle, but it's an engineering constraint. So if you have this engineering constraint, you still want to do full sky coverage as homogeneously as possible, and also because we have a different accuracy in the scanning direction and cross-scanning direction, we also not only want to cover everything, but we want to cover every point every time from a different angle, so that you get the errors in a symmetric way for all sources. So how do you do it? You spin the satellite, one spin 6 hours, so you can get a sweep of the sky. The spin axis is precessing in a 70-day cycle, and the spacecraft is at L2, so it goes around the sun in 1 year. So if I show this one, this one is just a simulation how this guy is going to be scanned by Gaia. So this is 10 minutes of observation. You see the first streaks of the 2 telescopes. So I just put the film rolling. It shows the ecliptic plane, where is the sun, and the 2 telescopes, and the spin axis. And then it starts to observe. So it's first making the circles, the precession. You see that the spin axis is moving a bit. So the precession is taking care that your circles are always doing a little bit next to the previous one. After 2 days, this is now the first half a year. I speed it up. So you see that the whole sky will be covered in fully in the first half a year. And then you just go on for the rest of the 5-year mission and fill the sky. So what you see from this one is that it's not perfectly homogeneous, unfortunately. The ecliptic plane is the difficult thing. So you will have at ecliptic plane or close to it, you will have regions where stars are observed only 40 times, so that's the blue areas. Average on Gaia is every source is going to be seen 70 times. And then you have these sort of high density regions where you have more than 200 sightings of sources. It's not that on those places you are going to get better astrometry, because the angle is there always the same, so you don't really gain. But for something like variability studies, it provides an interesting sample, of course.
Is there a radial velocity for every visit?
So the radial velocity is, because it's only half of the focal plane, so it will take more time. So on the average, for the radial velocity, you get 40 observations per target. Data processing. So this is done by our colleagues. I see a few here in the audience, but it's not a surprise because they are everywhere. It's basically because optical astronomy has tradition, so you have people who are interested to do it in most countries. So in the DPAC consortium, we have members of almost all European countries, some countries more than others. Just a little bit of the challenge these people are facing, so please some respect to them. 1 billion objects observed 70 times, 5 years, so if you do the calculation back, it's 40 million stars every day. And because there are 10 CCDs in a row, so we are talking about, on average day, it's 400 million measurements they have to deal with. And including weekends, so Monday when you come in, you have 1.2 billion objects measurements to worry about. And if you have a long weekend, you have 2 billion measurements. So don't take long weekends. Spectroscopy, smaller field, 150 million stars. We are talking about 10 million spectra a day of 3.3 million stars. So I think if you have a ground-based program, I think if I take the Chinese Lamost, I think that the idea is 10 years to do 10 million stars, I think. So that's going to be in a few days. I will downplay that a little bit in a later slide. Now for the performances, the astrometry, parallax performance. There is a flat part for the bright stars from 6 to 12, 13. And what is this flat part? The flat part is that at a certain point, it's a dynamic range issue. Even the 6 to 12 magnitude stars, they are too bright for Gaia. So what do? You have a mechanism where you are, at the moment when there is a sky mapper measurement, it estimates the magnitude. It's already saying, this is a too bright star. In order to measure this star, I have to limit in the future CCDs the reading area to part of the CCD only. So what you are doing, you are stopping actually when the star is being observed. You put a gate, electric gate on the CCD, you stop the flux, and you start integrating again. So you use only a small part of the CCD. So that's the only way how you get the dynamic range extended from 12 to 6 magnitude. For astrometry, you get the best result if you're always operating very close to the saturation. So in a way, you have the highest statistics. So here, in this flat area, the balance is how many of different gates we dare to put, because you have to calibrate every gate. So if you put very few, then you have a very wavy kind of behavior. So when you're close to saturation, you are sort of 5 microarc second parallax error. But you cannot make too many gates because of calibration. So we still have to decide precisely, but roughly in that domain, we are going to be below 10 microarc second. And then from 12, 13 up to 20th, it's just you are reading the full CCD, and at certain you are just getting less and less photons, so your noise goes up. And the spread here is the uniformity issue of the sky. But so we are at 20th magnitude, we are at 300 microarc second parallax error. Just to remind, Hipparcos was roughly 1 milliarc second in this one. And maybe sort of interesting to note, if you read the LSST numbers, the estimate is that for LSST, the floor, the best you can get for parallax error is 500 microarc second. So it's roughly the point where Gaia at 20th magnitude with 300 microarc second is hitting what you do from the ground, at least. On paper, you can do it from the ground. So it's about the optimum point, what is worth doing from space and what is better to do from the ground. It's around 20. You could argue, maybe we should do 20.5, maybe. Just a little bit, what does it mean? So if we think that this will be our Milky Way galaxy, we somewhere at the outskirts of it. For a solar type star, 1% parallax error, it's in the solar neighborhood. And obviously, if you can tolerate 10-20% errors, your space you can explore is increasing. So you start to get sort of a part of the galaxy is explorable for solar-type stars. If you put some extinction in front of it, it gets tougher, obviously. But if you really want to do the galactic structure, then you are not going to do solar-type stars. You look something which is intrinsically brighter. So you take a giant, a K-giant, and then if you look in suitable directions, so half of the galaxy at 10% accuracy distance determination. Just some sort of funny numbers. So if you take the parallax, I mean, just here is the scaling of factor of 10 when you get to the first star, Proxima Centauri. 1.30 parsec, parallax 769 milliarc second. It's a 13 magnitude star, so it's just in the bright domain for Gaia. So that's an interesting, it's a sort of faint star, but it's bright still for Gaia. It's a bright star. The Gaia will give its distance to 1.30 and 3 more digits with a 6-digit accuracy. Of course, you can sort of ask, do we even know the constants of physics to that accuracy? So it's a little bit of paper exercise. But the scientifically important thing is that if you look now, how many stars are known to 1% accuracy parallax? So it's 719. One could think that's not bad. That's a good sample. But it will be a little bit bigger with Gaia. So estimate is that the parallax accuracy for 1% will be about 10 million stars. And if you look the whole plot, so 0.1% accuracy, some 100,000 stars. Even if you're happy with 10% accuracy, you are having a sample more than 100 million stars from Gaia. So I think it will be quite an impact on the understanding of stars. Now, photometry, just a few points. First, the G band. So that is actually not really the photometric band, it is the astrometric band. And what is the purpose of astrometry? You just try to collect as much photons as possible, because the only thing what you want to do is to get the location or centroiding of the star. So it's a very broad band. Then we have the photometers. So if we forget about the prism part, just we look the whole band. Then we have the blue band. So it was from 330 around till 680, and the red band will a little bit overlap, 640 to about 1000 nanometers. So you can, of course, you could think that here is a 3-band system. So if you say that, okay, I don't care about the prism, but of course, the blue and the red, you should think that you can arbitrarily select your filters within that band because they are done with the prism. So you have spectro-photometry there. If you look a little bit the photometric accuracies one is getting, again for the bright stars where you are really close to this, operating close to the saturation, I think we will be even in the end totally dominated by systematics. And obviously for the blue and red, so if you instead, you are not using the integrated band, but you take some part of it, which is astrophysically important, obviously your accuracy goes down because you have less photons. But sort of talking about millimagnitude transit, and of course the G band, because it's broad, it has an incredible accuracy, and especially for variability studies, it is of course an excellent band, because it will be very, you can see very small variations. Sort of simulated what kind of spectrophotometric features you are going to get from stars. So here it is stars going from the blue stars towards red in the blue part and in the red part. So you get the sort of shape, rough shapes of the spectral energy distributions. These are for 15 magnitude stars. And what one thinks that what is possible to do with these 15 magnitude stars is extinctions to 0.1 magnitude, gravities 0.2 dex, metallicities 0.2 dex, effective temperatures roughly 200 Kelvin. That's about where you get. And of course, so it's not the accuracy, but that you have hundreds of millions of stars in this accuracy. That's the key.
Sorry, Timo, what's the resolving power? Is it 20, 10?
Yes, 10, 20, depending. It changes a little bit across the wavelength.
You get extinction to a tenth of a mag with 2 bands?
No, you use this shape. So you have a resolution, intrinsic resolution through this band, roughly 10 to 20, and that's where you get it. Spectroscopy, just now a single one pass. So what you see is that for bright stars, we are at the signal to noise between 10 and 100 until about 11th magnitude. The jump, what you see here, what is happening from 6 to 10 magnitudes, the stars are observed with the full resolution 11,500. After that, on board, one is doing a binning in order to decrease the readout noise. So you lose in resolution, you gain in signal to noise, so you gain in getting the radial velocities better. And if we pay attention to the end part of this plot, you see that we are talking about indeed a single observation, signal to noise 1. So that's, I come back to my statement, I said 10 million spectra a day. Of course, many of the spectra are going to look like noise. It's only that you wait for 5 years, you combine them all, that you get the real spectrum where you can get the radial velocity. And when you're at the faint end, radial velocity is the only thing you get from spectra. So here you can roughly see 11, 12 magnitude. That's spectroscopy, as most people think what spectroscopy is. The last part is radial velocities.
So if you have a binary with a 5-year period and all you have is noise, how you combine?
Then you will get noise. Yes. So what can you do? So for the photometry, that was providing the astrophysical parameters to a reasonable accuracy for large sample of objects. Here we are talking about spectroscopy for the bright end. You get the higher accuracy, you can get more astrophysical parameters, but it stops sort of 12 magnitude, so we are talking about a sample of 5 million stars. I think the good thing of the spectroscopy is that it's going to be totally unbiased. It's just what Gaia observes, so there's no clever thinking, which always actually turns out to be not so clever, in advance selecting which are the 5 million sources you should observe. It's just Gaia observes them all. And then the elemental abundances, that stops a little bit earlier, estimated 11th magnitude, so you need at least the signal to noise 10 at single sighting. And then you're talking about sample of 2 million stars. And the radial velocity, so that was the spectrometer is called radial velocity spectrometer, so it's a fair name. We have the flat part, which is really the systematics, estimated at 1 kilometer per second level. And then, so clearly for blue stars it's tough, because you are observing at the wrong wavelengths. For red stars it's easier. And you have the flat part extending to even sometimes to 15th magnitude. And then it goes very steeply up. So at the faint end, we are talking about velocity accuracy, radial velocity accuracy, 15 kilometers per second or so. This is a bit a busy plot. It tries to combine, it's also, I put it in for given the topic of this meeting. So if you're interested in velocity accuracy, so the 1 kilometer per second radial velocity accuracy is maybe not sufficient, but when you do very good proper motions, you are looking the velocities on the plane of sky direction. So these plots, maybe you have to think about it more. You can, if it's interesting to you, you can look it up. It's one of the weekly pictures on our website. But just very quickly, so you can see that if you are sort of at the bright end, 11th, 12th magnitude stars, so actually your velocity accuracy is better from proper motions. You are below the 1 kilometer per second for most types of stars. if you go to fainter ones, then somewhere maybe at 15th you have the sort of bending point that you are about the same accuracy for red stars, both in radial direction and from the proper motions in kilometers per second. So this plot is taking into account the error also we get for the stars in the distance determinations, because that's part of the, so it's a bit complex thing. Same plot, looking a little bit differently. So now the axis is here in distance. So you can think your cluster association, which distance it is. You go to the distance, if you have something with 500 parsec. For most stars, you are at the sort of 0.2, 0.3 kilometer per second accuracy from the proper motions. So you are better off in the sky, plane of sky direction than from the radial velocity. And of course, I mean, even that, if you look 1 kiloparsec, 2 kiloparsec, one few kilometers per second, I mean, you are still in quite a high level of accuracy. Okay, let me speed up. Clusters for Gaia. Let's take a real challenge. 30 Doradus, R136. The worst you can think. What was done, this is a Hubble image, of course. There is a work on this one made with multiple different exposure times and ditherings, and in order to get the full census of this one with 39 millisecond pixels. So what was done by my colleague Jos de Bruyne, he took all those point sources. So forget about the image, just get the point sources. We have a full Gaia simulator, put it in a simulator. The simulator is running the onboard software, exactly the same software what this Gaia is going to run in space. And this is what you get. So you get the yellow ones are the stars, which are from the Hubble Space Telescope. All the green little windows are where Gaia makes a detection. So you see immediately that sort of most of it is green. There are some empty spots. So this is one of the handicap of very dense clusters. When you run out of resources, if there are too many stars, bright stars, you don't have enough memory capacity on board to do it. Now this one is 4.4 seconds of Gaia observations with one CCD. So what was done with the other CCDs and the rest of the 5 years, I will not show. This is 4.4 seconds. I think it's not too bad. And if you think that Gaia is going to do the different angles, so the bad area is going to rotate and vary. So in the end, you will get the full census. You will miss some, but not too many. Just very quickly, so this is what the windows look like. Faint stars are detected, so Gaia could go deeper, but we have the 20 magnitude limit. You get windows for the stars, and it looks okay. If you go a little bit denser region, you can see that it gets a challenge to disentangle all the sources and all the windows.
How big are the windows?
The windows are, what is observed is, it depends on the brightness again. But for the faint ones, there is also cross-scan binning. So you see all these lines. So we are measuring 12 or 18 depending on the brightness, and what you get to ground is for the faint ones 6 pixels. And the cross-scan is just collapsed together.
And on the sky, the angle is?
Now in scan direction 6 pixels, 6 times 60 millisecond. I don't see the time, sorry. 10 minutes, yeah, good, thanks. So it's 6 times 60. What you see actually, I wanted to show here, sorry. There is one, the simulator puts cosmic rays in it. So it's also to test that you don't get cosmic rays downlinked. So it seems to work at least in one case. But bright stars, we get the full, all the pixels. So you do get the point spread function for bright stars. Okay, I think. Yeah, and then just simply some statistics. So if you take the black histogram is what the Hubble Space Telescope was doing in this field. And then the green one is what Gaia recovered with one CCD in one observation with 4.4 seconds of time. So if you then rotate, of course, it's not going to be the exactly the resolution of a Hubble Space Telescope. So in the end, the greens will never hit the black. But I mean, of course, the Hubble is also not complete. I mean, it's such a dense cluster. It's a matter of where do you stop. I noticed that in this school, the poster was of Orion. So first I was thinking Orion would be a better example, but it's not, because it's not a challenge. For Gaia, it's empty. The stars are so far away from each other that it's not a problem. It's just full completeness. So this is a challenge. So you can think if this can be done at 50 kiloparsec, in one of the densest clusters, that if you are happy to take a cluster a little bit closer, a little bit less dense, you'll be fine. Service module, 10 minutes. I think I will not start talking about technology. Let me just say something what I do want to say. It's not the launch, but we had the first Soyuz launch from Kourou with exactly the same configuration as Gaia is going to do, so with the upper stage and everything, and it was successful. And just last week, we got the analysis of that launch, so all the vibration frequencies and strengths, and they were exactly as calculated. So this shaking test, what I'm showing now here on the torus, was done with the right vibrations. And I just like it because if you look this very carefully, you see that things are moving, but in the mirror, you see the torus is not moving, which means that on the optical bench, the mirror it's fixed. So even if you shake it, it just shakes with it. It doesn't move. So it's exactly stable. This took place already a while ago, and it went all fine. So, let me conclude. I think, I hope I convinced orders of magnitude improvements. I hope I wasn't too upbeat in the... schedule has been slipping. Now it has stabilized. I think we have no technological problems, but this schedule has also there is no fat at all. This is the working schedule. So every time something happens, we move it. So you have always this political thing, launch, you say a date, but everyone knows it's not that date. But for Gaia, I mean, I'm very happy with our project manager. He's saying the date is what the date is. And today it's August 2013. If everything works as planned, it will be August 2013. If something happens unexpected, alignment problem, test problem, the date will move, and then we will put it on the web. And then you know it. Science alerts early on, intermediate releases starting roughly 2 years after launch. We have half a year commissioning time, and then we have to cover the sky, and then we need a little bit of time to think what to do with 1 billion objects. And well, just get ready. I think astronomy will change. I think you are in a good topic at a good time. So I think that there will be some major advances made in stellar cluster understanding. I stop here and thank you for the attention.